Next application is an evaluation of expressions where we are going to use a stack again. Now let's talk about evaluation of expressions. First of all, what is expression and what is evaluation? So expression is not that hard to understand. Basically, it's some equations. Something like a 3 plus 5 or 3 times 2 plus 7. Okay, these are expressions. And if we use a symbolic expression, then we can have a plus b, okay, or a plus b times c. Okay, these are examples of expression. Then what is evaluation? Evaluation is actually calculation of this expression. So given this one expression like a 3 plus 5, then when we evaluate this expression, then we will get 8. Okay, so it's basically calculations. So in this slide, we want to evaluate an expressions. Okay, so basically we want to implement a calculator. So given an expression, so we will calculate. Okay, so in the expressions, we have some elements or tokens. Okay, first element is operator. So we can have a plus, minus, and multiplication, divisions, and modular, and etc., etc. So if you want, you can have some other operators. Okay, next, operands. As I said, if we have a symbolic expression, then we can have some variables like x plus y. Okay, but usually, if it is not symbolic, then usually the operands are numbers. Okay, and then parentheses. So with this parentheses, we can change the order of evaluations. You know that, right? So if we have a parenthesis, then we will evaluate the inside of this parenthesis first, and then we will look at the other. Okay, so we have some examples on this slide. Okay, then and also we can use a tree structure to represent our expressions. So basically, we have operator, and then we have operands. So operands are kind of children, and operator is a parent in this tree structure. So as I said, in this evaluation of expressions, the important issue is the evaluation order of the operators. So we have to figure out which one will be evaluated first, and then which one is the next, okay? That's important things. As long as we know that order, then evaluation is not a problem. Okay, so we can just follow that order, calculate it. So when we talk about the evaluation order of operators, then we have to think about some features. First one is precedence. Okay, precedence describes the order in which the operators are evaluated. So basically, as you know, the multiplication and the division operators precede plus and minus operators. Okay, so when we have a 3 plus 2 times 5, then we have to multiply 2 and 5 first, and then we will add 3. Okay, 3 times 2 times 5. Then we will multiply first because it precedes the plus operator. That's what precedence says. Okay, the next one is associativity. Okay, so this associativity describes the order in which the operators with the same precedence are evaluated. So when we have in this slide, I have one example, 378 plus 7 minus 378. Then plus and minus, they have the same precedence. Okay, then we will evaluate the left one first and then the right one. Okay, so 378 plus 7 will be evaluated first, and then we will subtract 378. Okay, so we will follow this associativity order. But here is an interesting issue. As you can see in this example, when we evaluate these expressions, we know the answer is 7 so easily because we don't actually evaluate 378 plus 7 because we can see that here. We can see that we have a 378 and we have minus 378. So we just apply this expression. We just evaluate this expression first, and then we have 7. But to computer, we cannot change the order. Okay, so we have to follow this associativity and precedence exactly. Okay, so we we can just evaluate the right one first if we have the same precedence. So we can evaluate 7 minus 378 first, and then we can add that to 378. There's no problem. But we can evaluate the left one first, or we can evaluate the right one first. There's no difference at all. But to computer, we have to choose one directions. Okay, so now let's evaluate the leftmost one first, and then evaluate the right one and the right one. Okay, and when we have a unary operator, then it goes from right to left. Okay, and if we have a prefix operator, then it goes from right to left. Okay, and as you know, when we have a parenthesis, then it changes everything. Okay, it can override all the precedence and associativity and everything. Now there is another important issue in these evaluations. So basically, we'll talk about 3 different notations. First one is infix notation, and second one is postfix, and the last one is prefix notations. So what is infix notations? Basically, when we use some equations in the mathematics, then all the notations are basically infix. That's most common to us. Okay, so it's a binary operator in between operands. So a plus b, or 3 plus 5, 3 minus 2. So these are infix notations. Okay, so the operator will work on the left and right operands. Okay, then the next notation is postfix. In this case, instead of a plus b, we have a b plus. Okay, so we have 2 operands first, and then we have operator. So operator follows 2 operands. So why do we have this one? Because this one is much popular. Okay, much popular in the computer system. So in computer, postfix is much easier than infix notations. Okay, we will see that later. And then the last one, prefix notations. Okay, so we don't have a prefix notation for the expression usually, but it's something like a function. Okay, so operator goes first, and then 2 operands follow. So something like a function call. So in this slide we have plus ab, and it is something like a plus is a function, and ab are 2 parameters. So the function call is something like a prefix notation, but we don't care this prefix notation that much in this class, so we will focus on infix and postfix notations. So basically, in infix notations, we will read the left child and parent and the right child. Okay, so when we have a tree structure to represent our expressions, then if we read the left child and the parent and the right child in that order, then it generates an infix notation. If we read the left child and right child first, and then if you read operator, then it will generate the postfix notations. So here's an example. So we have A and B and C in the child in the leaf nodes, and then we have a plus and star. Okay, then if we read this tree in the infix notations, then it is A plus B times C. Okay, and then if we read this tree in the postfix notations, then it is A, B, C, and star and plus, because we have to read the child the children's, the left child and right child. So we have to read A first, and then we have to read this subtree. Okay, in the subtree we have to read B and C first. So we have to read B and C and then star, and that is the right child to the plus node. Okay, so that's why we have to read A, B, C, star, and plus to make a postfix notation. Okay, again, the infix notations, we have to read the left child and operator and the right child. So we read A and plus, and then the right child, which is a tree again. So recursively, we will read B and star and C. Okay. Okay, now let's compare infix notation and postfix notations. And also, let's try to translate between these two notations. Okay. So infix notation is easy to understand for human. So we are familiar with infix notation, but postfix notation is not so much familiar to us. So it's a little hard for us to understand. But the postfix notation is much easier to computer, and it doesn't have any parentheses. So in this table we have lots of examples. In the postfix notation we don't need parentheses at all, but in infix notation we need sometimes. If we want, we can have parentheses. And in the postfix notations, the operands order in the postfix is the same as in infix. So look at these numbers: 2, 3, 4, 2, 3, 4. So we don't change the order of these operands. In the second line we have A, B, 5 in the infix notations. In the postfix notation we have A, B, 5. So if we look at just operands, ignoring the operator, then the operands keep the same order. Okay, and then next, the order of operators is the same with the evaluation order. That's the beauty of these postfix notations. Okay, in the infix notation, it's a little complicated. Which operator should go first? Okay, we have to check the precedence, and then we have to check associativity, and we have to check the parentheses. But in the postfix notations, there is no confusions. So the order of this operator is the order of evaluations. Look at this one. The first line, in the infix notation, we have a 2 plus 3 times 4. And we know 3 times 4 goes first, okay? Because we are familiar with these notations. But in the postfix notations, there's no confusion at all. So star is first. Okay, star is the first operator, and the plus follows that, which means we will evaluate this star operator, multiplication operator, first. Okay, let's try the next line. So in the next line, A star B plus 5, and infix notation, we know how to evaluate. And in the postfix notations, star is first. Okay, so we will evaluate A times B first, and then we will evaluate the next operator. How about the third one? We have parentheses. It's a little complicated, right? So we focus on this parentheses. So we will evaluate this 1 plus 2 first, and then we will evaluate the star operator. But in the postfix notations, we have plus first. Okay, before the plus is ahead of this star operator, because the plus should be evaluated first. So in the postfix notation, we don't need any parentheses. Okay, so let's try to convert the infix notation to postfix notations. So we have A times B divided by C. Then we just put some, we have to put the operands first, and then we have to check which one goes first, which operator goes first. So star operator goes first. So A, B, next we should put star, and then after C we have to put a division operator. Okay. In the previous slide, we had some examples of infix and postfix notations, and we tried to convert the infix notation to the postfix notations. So that's not that simple. That's not that straightforward. So we'll talk about that later. Okay. And then in this slide, we assume that this expression is given in the postfix notation. Okay, if the postfix notation is given, then how can we evaluate? So that's the simple. So we will focus on that simple step first, and then in the next section we will talk about the conversions. Okay, so first, so using the stack, we will evaluate the postfix notations, and that is straightforward. Okay, so basically scan from left to right. Okay, we assume that this is postfix notations. So we have these expressions in this blue color. Okay, and then we scan from left to right, and if the current element is an operand, then push it to the stack. And if the current element is an operator, then pop two operands and perform the operation and push the result back to the stack. That's a simple procedure. Okay, so with this example, then we'll try. So the first one is the 6. Okay, then we push because this one is operand, and then second one is 2, so we push because this one is operand, and then next one is operator. Then we pop two elements. So in the stack, we have 2 and 6. So we pop two operands. Now we evaluate this 6 divided by 2. Okay, and then the result is a 3, and then we push a 3 back to the stack. Okay, so now we have a 3. So it looks like a 6 divided by 2 in the stack, but actually it is a 3. Okay. And then next one is a 3, which is an operand, so we push. So now in our stack we have a 3 and 3. And then next one is a minus, which is operator, so we pop two operands. So we have a 2 3s. So we evaluate this operator. So now the result is 0. So we push the result. We push 0 to the stack. And then next one is operand. Next one is 4, so operand. So we push. So now in our stack we have a 4 and 0. And then next one is also an operator 2. So we push. So in our stack we have a 2, 4, 0. And next one is the operator. So we pop two operands. So 2 and 4 are popped. So we evaluate 4 times 2. So we push the result back. So now we have 8 and 0. And then next one is plus, which is operator. So we popped two operands from the stack. So we pop 8 and 0. Okay, and then we apply this plus operator to 8 and 0. So now the result is 8, and we push 8 back to the stack. So now we are done. So in the stack we have only one number, which is the result of this evaluation. That's it. So we have two examples. So calculate the following expressions using a stack. So you can draw a stack on your paper and try to evaluate these expressions. Okay, that's kind of practice.